Okay, we have here to another integral from the UNSW Integration Bee 2020. This is from semifinal 1, problem 2. We have the integral from 0 to 1 of x to the m, ln x all to the n, dx. Okay, I thought this was really interesting. I've probably done problems like this before with, definitely with m and n equal to 1 or 2. One thing I want to note before we get started is we have this condition on here that, just want to note that m and n, the exponents here, those are going to be positive integers. So I definitely think there's a few ways to approach this, but the way I went about it was just trying to make a substitution, just a basic u substitution to start for ln x. So we'll just go ahead with this. We'll call u equal to our ln x. And then what I want to do is just isolate x. So what I can do is just rearrange this with the properties of the logarithm and write this as x equal to e to the u. Then I'll just get my derivative. So dx is going to be, derivative of this is just going to be e to the u du. Then from here, let's just go ahead and substitute. So first, we'll update our bounds. Plugging in 1, natural log at 1 is just going to be 0. Plugging in 0, natural log at 0, that's going to be minus infinity. Then substituting everything else, x is going to be e to the u. So I can write this term as e to the mu, just multiplying in the m on the exponent. ln x is u, so this is going to be u to the n. Our dx is going to be this, so we'll have e to the u du. But then I can just combine, we get the same base here, so I can rewrite this and write this exponent as n plus 1 times u, and then we'll just copy down everything else. So I think in order to change this exponent here, I'm just going to do another substitution, and this is going to be a little unusual, so bear with me for a second. We'll do the substitution, n plus 1 times u. I'm going to set it equal to minus t. Of course, we could rearrange that and write that like this. And I also could solve for u, so I could write this as u equal to minus t over n plus 1. Take a derivative, so our du value, now n plus 1 is just a constant, so this is going to end up being minus 1 over n plus 1 dt. So now we'll just go ahead and substitute again. It's getting kind of confusing over here, but we'll take the 0, we'll plug it into this one. Plugging 0 in for u here, my t becomes 0, so this is still 0. Now if we take minus infinity here, minus times minus gives me plus. This is going to positive infinity as long as m is greater than minus 1, but we have this condition that's positive integer, so we don't really have to worry about this, so this is always going to infinity. Then this here is going to become e to the minus t, and our u value is this thing, so this is going to be minus t over n plus 1 to the n. Then du is this, so we're going to have minus 1 over n plus 1 times dt. Well, I can take this minus sign here. I'll use that to flip my bounds. So now we're integrating from 0 to infinity. And then this term right here is just a constant that I can take out front of the integral. And I can take out some of this too, because I can rewrite this. I can split this up and write it as t to the n minus 1 to the n. And then we'll have, I could write it a few different ways, but I could write it like this with n plus 1 to the n here. So then doing that, all this stuff is a constant value that I also can bring out of the integral. Okay, so now we can rewrite and bring this up front of the integral. This first part, so we'll have minus 1 to the n over n plus 1 to the n. But then this piece is also a constant coming up front, multiplying n plus 1 in the denominator by n plus 1 to the n. This gives me n plus 1 to the n plus 1. Then at this point, the integral is actually pretty well simplified, because now we'll have, don't forget this, we'll have our t to the n, we'll have e to the minus t dt. But the good news about this here is just the gamma function. Okay, we have this definition for the gamma function down here at the bottom. I have it kind of shifted. You could write this as gamma of n, with the n here being n minus 1. It doesn't really matter. So for our definition for the gamma of n plus 1, we have this is exactly the same thing as our integral right here. So this is gamma of n plus 1. But again, at the beginning, we said that our m and n values are positive integers. So for integer values, we can just express the gamma function in terms of factorial. So we can just write this actually as n factorial. So this whole thing here is just n factorial. So putting it all together, this gives us our formula for the solution. So we're going to have minus 1 to the n times n factorial. And this is going to be all over this part, which is just m plus 1 to the n plus 1. And that's it. So there you have it. Good problem from UNSW 2020. Thanks everyone for watching. Have a good day.